Look at a modern consumer drone, and you will see a pristine machine hovering in near total silence. But military aviation operates in a different reality. Deep behind enemy lines, high-endurance flight relies on grimy, heavy-fuel piston engines that shake violently on a test stand. Purely electric flight is precise, but it hits a hard mathematical wall after 60 minutes. At that point, the batteries are depleted, and the power source effectively becomes dead weight that the aircraft must continue to carry. This constraint is dictated by energy density, the physical law that determines exactly how much raw power can be packed into a given amount of mass. This chart compares the specific energy of two power sources. A lithium polymer battery holds roughly 250 watt-hours per kilogram. Kerosene fuel holds 12,000. That is a 50-fold difference in energy capacity between a single drop of liquid fuel and advanced electrochemical cells. If a mission requires a drone to loiter over a battlefield for 12 hours, batteries cannot store the required energy. Survival at those durations requires the raw power of controlled fire. You might expect these small engines to run on specialized high-octane racing gasoline, but in a forward military deployment, transporting a separate supply of volatile gas just for drones is a logistical liability. Instead, operations are bound by the single fuel mandate, requiring every combat engine to burn the exact same kerosene-based fuel, typically JP-8 or F-34. This forces a 50-pound surveillance drone to share the exact same fuel supply used by a 70-ton armored tank. Heavy jet fuel is incredibly thick. When poured into a tiny two-stroke engine, it creates carbon deposits that rapidly destroy the internal cylinders. The solution is air-assisted direct injection. By using pressurized air to shatter the heavy kerosene, the system atomizes the liquid into an 8-micron mist that the small engine can ignite. Building a small engine that can digest heavy military kerosene solves the fuel crisis, but managing that combustion creates a new physical threat. Heavy fuel engines generate extreme structural vibrations. The movement of the piston sends mechanical shockwaves through the airframe at frequencies reaching up to 500 Hz. These oscillations travel directly into the payload, where they physically blur the optical targeting sensors and degrade the resolution of thermal imaging equipment. The vibration also attacks the drone's navigation hardware. If those frequencies reach the delicate gyroscopes and accelerometers in the inertial measurement unit, they cause immediate and fatal flight navigation errors. To counteract this, designers use dynafocal mounts and elastomeric shock absorbers. These intricate wire loops physically decouple the shaping engine from the autopilot module. Reliability in these airframes depends on a total mechanical separation between the vibrations of the motor and the sensitivity of the navigation hardware. Once the drone climbs to 30,000 feet, it faces a new environmental enemy: the thinning atmosphere. Combustion requires a precise ratio of oxygen to fuel. As air density drops at high altitudes, a naturally aspirated engine loses its ability to pull in enough oxygen, and the engine slowly suffocates. The fix uses the engine's waste. Hot exhaust spins a turbine, driving a compressor to force dense air into the intake. As pressure changes, a mechanical wastegate opens, bleeding off exhaust to prevent overpressurizing as the aircraft climbs. Maintaining power in thin air is an engineering fight to force an oxygen-starved engine to breathe. These engineering feats are required because tactical drones often operate where infrastructure is non-existent. Without a runway, they are fired off pneumatic rail launchers. This mechanical endurance is necessary for covert surveillance over the vast, remote distances found in hostile environments. The next stage of development combines the benefits of both power sources into a parallel hybrid propulsion system. The drone uses the raw power of liquid fuel to climb and cruise, simultaneously using that kinetic energy to charge its onboard batteries. Once over the target, the combustion engine can be shut down. The drone switches to its batteries, gliding over the objective in absolute electric stealth. The hybrid system turns the rigid constraints of physics into a tactical advantage, using high-density fuel to reach the objective and silent electrons to survive it.